Dear Chairman, dear colleagues, after so many years of missing the conference, I am very glad to be with you again, although distantly, but mentally with you. This is a great honor for me to get so high appreciation of my work and the work of my colleagues. I am thankful for this opportunity to present you today the story of coherent nuclear fluorescence, to discuss with you the main properties and applications of this beautiful phenomenon, and especially to remember the scientists who paved the way for development of this new area in Meßbauer spectroscopy. Let me start with a message from Democritus, a good one for any researcher. The point is not in completeness of knowledge, but in completeness of understanding. Rudolf Meßbauer brilliantly implemented this phenomenon. He had not only brought us the new knowledge, but gave a clear and precise explanation of his finding. The effect he discovered gives gamma quantum a chance to carry away into space and time the coherence inherent to a nuclear radiative transition. The wave packets of about tens of meters in length can bear 10 to 13, 10 to 15 strictly phased oscillations. Isn't it an amazing example of the coherence preservation? Coherent nuclear fluorescence became a real miracle of nature, discovered by Meßbauer. Immediately after the Meßbauer discovery, it became tempting to observe how it reveals itself in nuclear resonance scattering. Initially Black and Moon, and then Bernstein and Campbell observed interference between electronic and nuclear scattering channels. Most impressive it was seen in the Meßbauer spectra of total reflection from an iron mirror. The interference manifested itself in the dispersive shape of the resonance lines. The dispersive because on one side of resonance the interference of two scattering channels was destructive, whereas on the other side it was constructive. A bit later, Black, Longboth, and O'Connor observed for the first time the Bragg reflection from nuclear ray in the crystal. This way, the absolute coherence of nuclear resonance scattering was proved in energy domain. Using the delayed coincidence technique, the two groups of physicists, Wu et al. And Lynch, Hall, and Hammermesh, investigated the temporal passage of gamma rays across the resonant targets. In both experiments, bits of the transmitted intensity were observed. They were evidencing about the interference in time of the source and the forward emitted by target gamma radiation. Due to constructive interference at certain times, the transmitted intensity appeared to be greater than in the incident beam. Thus, also in time domain, the coherence of nuclear resonance scattering was revealed. After the first inspiring investigations, the systematic research began, both in theory and experiment. Yuri Kagan, Alexander Afanasyev in Kurchatov Institute, George Trammell and Jim Hannon in Texas University started development of theory of nuclear resonance scattering of gamma radiation. Using different approaches, they laid a theory basis for the coherent interaction of gamma rays with ensembles of nuclei, put forward new conceptions, and predicted many new physical phenomena. One should especially stress the idea of nuclear delocalized excitation in nuclear ensemble, the possibility of the complete suppression of inelastic channels, and, what is of special importance, the possibility of great enhancement of radiative channel in nuclear resonance scattering. As it concerns the experiments, systematic work started in the middle of the 60s in the two groups of Kurchatov Institute, one headed by Wojtawecki and the other by Sklarevsky. For studies of Bragg scattering, the perfect crystals enriched by resonant isotopes of tin 190 and iron 57 were prepared. A whole number of the coherent phenomena were observed. Among them, interference of electronic and nuclear channels, anomalous transmission of resonant gamma radiation through a thick crystal, Bragg reflections in backscattering geometry, pure nuclear diffraction widely applied in our days, pure nuclear Lauer diffraction, suppression of internal conversion, resonance properties of nuclear ensembles, and many others. In the 60s, several other groups of scientists joined this activity. One should mention Belyakov and Avazyan, who developed the theory of pure nuclear scattering, Kuzmin and Andreeva, who actively worked to develop the theory of mesbahorography. In the 70s, a collaboration between Kurchatov Institute and Technical University of München was established. This was a very productive collaboration, lasted for more than 30 years. In this picture, you can see several members of the joint group. For about 15 years, the described activity lasted within a rather close circle of people. Overcoming the great difficulties with the low brightness of radiative sources, the new methodics were developed, new observations were performed, and new results were obtained. One of our referees wrote to me that time, "Your work is looking like a curious and exciting game, also in fairy but nano kingdom." To our pity, this was not only his opinion. Nevertheless, these efforts paved the way for future experiments with synchrotron radiation. Absorption spectroscopy, with the use of radioactive source, was dominating for a long time. Let's have a look what actually absorption does mean. A target containing resonant nucleus is attacked with resonant photons. One of them is found to be absent in the transmitted beam, what means absorbed by a nucleus and target. The energy of nuclear excitation can be released in the two ways, either transmitted to the atomic electron or given to a gamma ray photon, wherein both particles are emitted into 4 pi solid angle. So, as a matter of fact, an absorption of incident photon is related with the spatially incoherent scattering. What is essential for us to note? For most of nuclear isomers, the radiative channel plays a minor role in scattering event. As you are aware, for iron 57, it is only of 10% cases. This certainly was the main reason for skepticism about the suitability of the radiative channel in experimental research. But let us now consider what happens when the target contains not a single but many resonant nuclei. Imagine the shutter suddenly interrupts the beam. At that moment, quantum is ready to excite the target. Mesbah people are used to think that gamma quantum interacts with a separate nucleus, that one or some other. And this is natural because energy of gamma quantum is sufficient to excite only one, a single nucleus. With this in mind, seems to be incredible that quantum could interact with a whole ensemble at the same time. But this is the case. Indeed, such scattering events like forward scattering, total reflection, diffraction were observed. And this observation revealed that we have dealt with the collective phenomena where a single quantum is scattered by all nuclei. As a matter of fact, when scattering is elastic, there is no indication which nucleus has been excited. Using quantum mechanical approach, one should suppose that with definite probability amplitude, every nucleus is allowed to take part in the scattering process. The state of excitation delocalized over the system was called nuclear exciton. This conception was introduced by Tremel, Kagan, and Afanasyev. It turns out that we must speak about interference of all scattering paths, that is, multipath interference, the result of which, in this case, should be forward scattering. Well, now I would like you to show the experiment described here. It was performed in Kurchatov Institute. Almost black resonant absorber was used. After prompt chopping of incident beam, like here, a strong flash of intensity occurs behind the target. No doubt this radiation is released during free de-excitation of target. Pay attention, the delayed emission proceeds not into 4 pi, but in the forward direction. Evidently, we have deal here with the coherent response. Almost 100% of captured radiation is remitted in the forward direction. Thus, we got a clear evidence of great enhancement of the radiative channel, and the proof of the possibility of radiative channel to be dominant in scattering process. Now we consider the nuclear Bragg diffraction and its properties. Nuclear reflectivity function presents here a surface of complicated shape above the plane formed by angular and energy axis. In the range of Bragg angle, here it is, and near resonance it is here. A specific feature of nuclear diffraction is that reflectivity is a two-dimensional function. The angular dependence phi of resonance, this cut of this function, exhibits a rather narrow angular peak. In a similar way, the energy dependence phi of Bragg angle, this cut of the function, has a shape of usual resonance line. But while approaching the Bragg position, the resonance line is getting broader and broader. At the exact Bragg position, its width reaches several tenths of gamma, and the reflectivity at the resonance becomes nearly 100%. These are amazing consequences of the enhancement of radiative channel and suppression of the internal conversion. Eventually, this phenomena opened the door for using synchrotron radiation by Mesbaro community. In 1974, Stanley Ruby suggested to excite the 14 kV Mesbaro resonance in iron 57, using instead of a radiative source, synchrotron radiation, in order to populate the nuclear excited state. He has to struggle for years to develop techniques for separating the nuclear resonant X-rays from the overhanging synchrotron radiation background. The first successful experiments were carried out only 10 years later in Hamburg by Erich Gerdau group in 1985. To suppress the background, they had used a pure nuclear diffraction from yttrium iron garnet single crystal. With synchrotron radiation incident beam in resonance, the delayed nuclear gamma radiation was observed. This was detection of nuclear response in time domain. In addition, in energy domain, the spectrum of the delayed radiation was measured. The first successful experiment, as a trigger, sparked a burst of enthusiasm in study of nuclear resonance scattering of synchrotron radiation. Very soon, a fruitful collaboration arose between Kurchatov Institute, the Mesbaro group in Munich, and the group of Professor Gerdau in Hamburg. Jerry Hastings' group began to operate in the United States in the Brookhaven National Laboratory. Stanley Ruby group in Stanford Synchrotron Radiation Lab, and in 1993, the group headed by Rudolf Rufer was founded in the European Synchrotron Radiation Laboratory. At around the same time, the Seishi Kikuta group became active in the Japan photon source. describing evolution of nuclear exciton and target, one should regard a united system of currents and fields, which are dynamically coupled to each other, forming, in fact, nuclear polariton. How this coupling can be imagined? Let it be a target, and synchrotron radiation is about to excite it. Here is the state of nuclear polariton at the first instant of excitation. Red points indicate the new spatial distribution of nuclear currents, and blue points distribution of radiation field. You see, the probability of excitation is distributed evenly through target at the first instant, whereas the field amplitude is growing with thickness. And here are several distributions at the following times. In developing with time, fields and currents exchange by energy. It is well seen if we look through time at a given depth in target. At this point, the energy is concentrated in field completely. At the next point, in the nuclear system. Further on, vice versa, and so on. Interesting to trace the excitation of nuclei located on the opposite sides of target. At the input, it is described by exponential function, whereas at the output, by time-modulated function. This is because at the entrance, a nucleus exhibits free decay after the prompt excitation, but at the exit, a decay is induced by the field forward emitted from the upstream target. Let me dwell on some fundamental properties of the nuclear polariton. I will try to illustrate them with a few examples. We start with lighthouse effect. This effect was found by Ralph Roseberger and his colleagues. Phasing of excitation in space of target is determined by the plane wave of incident radiation. Since the phasing is preserved with time, the coherent emission of gamma quantum proceeds in the forward direction. By the same reason of keeping the memory of excitation, the target after being turned emits quantum in a new direction. Moreover, if the target were brought from one table to another, it would continue to emit radiation according to the primary memory of excitation. Imagine that target is separated now into two fairly distant parts. Nevertheless, the synchrotron radiation pulse traversing the targets creates a nuclear exciton extending over both parts of the system. Of interest is the possibility to modify a nuclear exciton by manipulating one of its parts. This is because the response of the system becomes very sensitive to the phase matching between the parts of the collective excitation. When A and B targets are of equal thickness, the carrier oscillations of their wave packets all time are in equal phase. Ultrasound vibration of one target disrupt the initial phasing given by synchrotron pulse. As a result, the forward emission from each target occurs independently. But already after the first period of the UAS vibration, phasing of packets is restored for constructive interference. At that moment, we observe a super-radiance from the system. In the case of unequal thicknesses, the carrier oscillations at phasing restoration may be shifted in phase by pi. The destructive interference occurs then, and a subradiance is observed. The time delay between dephasing of exciton and its restoration with resulting echo is more than 10 to 11 cycles of the nuclear current oscillations. Here we have deal with the remarkable evidence of the intrinsic phase correlation in the system of separate targets for so long time. Another remarkable example of nuclear exciton survival. In an iron-barrate single crystal, the internal magnetic field can be switched promptly, much faster than the thermal precession occurs. When making this after nuclear system excited by synchrotron radiation pulse, repopulation of nuclear levels occurs, with the end of practically stopping the coherent channel, forward emission in this case, at the time t prime. During long time, the system de-excites into 4 pi with the natural time. But at the moment switching back occurs, a strong flash of the forward emitted intensity is detected. In this way, the energy which was stored in the nuclear system was released. The phase memory about the initial coherent excitation of nuclei was kept for a very long time. The last and the former examples allow one to formulate some fundamental properties of nuclear exciton, and namely, whatever dynamical perturbation of the system occurred, translational or rotational motion of target, the target ultrasound vibration, magnetization reversal, provided they are homogeneous in space and time, the initial phasing of nuclear excitations in nuclear ensemble is preserved. The other example revealed that the internally matched nuclear exciton can be created in several spatially separated targets, in the scheme that allows to manipulate phasing of excitations between the targets. This property paves a way for the time domain interferometry with synchrotron radiation. Back to pure nuclear reflections, most effective to suppress harmful non-resonant radiation. The first observation of such reflection took place in 1969. There, antiferromagnetic crystal was employed. With this example, I would like to reveal to you the nature of pure nuclear diffraction. Let's consider first the electron diffraction. Imagine the unit cell with 2 iron atoms. Electrons interact with the electric field of incident radiation. Let it be p-polarized. Upon electronic scattering, electric dipole oscillations are excited. They develop in antiphase due to the choice of forbidden reflection. By this reason, they, being summed, yield no scattered radiation. Now to the reflection from nuclei. The decisive difference here is in multipolarity of transitions. In the nuclear case, it is magnetic dipole 1, where circular transition currents can be excited upon interaction with the magnetic component of incident field. Circular polarization of the excited currents is sensitive to orientation of local magnetic field. At the first moment, polarization vectors are directed oppositely because of the structural factor, yielding zero response at that time. But later, due to opposite orientation of the local magnetic fields, they perform the counter-rotation, producing the linearly polarized scattered radiation. Polarization of field is turned with respect to that of the incident beam by 90 degrees, from pi to sigma polarization. Considered pure nuclear diffraction provides the possibility to generate synchrotron Mersbau radiation. We turn to that issue now. Shown here is the surface of pure nuclear reflection from an antiferromagnetic iron-barrate crystal at room temperature. Magnetic field at iron nuclei is about 330 kiloerstat at this temperature. The angular cut of the surface at a distance from Bragg angle presents a Mersbau diffraction spectrum with well-resolved 4 lines of the hyperfine structure. Thus, at this temperature, the crystal excited by synchrotron flash should generate gamma radiation containing several distant energy components. Obviously, such a spectrum of the radiation source is inconvenient for spectroscopic studies. When the crystal is heated, the spectrum shrinks. In the critical range of the phase transition, magnetism disappears and the reflection is cancelled. But at the very vicinity of the nail temperature, the transition point, by applying a weak external magnetic field, it is possible to restore the reflection, with the spectrum containing a single line. Here we can see the reflectivity surface in these conditions. Within a rather broad angular interval, singular radiation is generated. With the use of this effect, the first synchrotron Meuse-Bauer source was created in ASRF in 1997. Later, a modified source was created in Japan at Spring 8. Presently, 4 sources are operating in ASRF, Spring 8, and DESI. The 2 are in preparation in Novosibirsk and Pekín, and the 2 are planned in Chicago and in Moscow. You see here the scheme of a beamline in ASRF, where the undulator radiation is converted into Meuse-Bauer radiation. As you know, synchrotron radiation comes in the form of series of short pulses. After nuclei are excited by a separate pulse, their eigen-glowing starts, coherent nuclear fluorescence. As long as the excitation is kept, the crystal glows and continuously emits resonant quanta. In this way, synchrotron Meuse-Bauer radiation is created. A key element here is an iron-buried crystal. The Meuse-Bauer radiation has remarkable properties. First, it is completely recoilless. Second, it propagates within a narrow solid angle. And third, it is entirely polarized. The absence of non-resonant background makes it possible to obtain Meuse-Bauer spectra with samples having negligible content of resonant nuclei. The directionality of radiation flux makes it possible to use the latter in the experiments on coherent scattering, total reflection, diffraction, and so on. The polarization opens the ways of using the radiation in polarimetry. With the help of Kirkpatrick-Baez mirrors, it is possible to focus radiation down to micron sizes and conduct research with small amount of matter under extreme conditions, by pressure, magnetic field, and temperature. When a research with the use of radioactive source gets boring or simply impossible, suddenly one remembers there exists a synchrotron Meuse-Bauer source. This is just the case of ultra-thin magnetic layers. In the work by Andreeva et al., the double spiral magnetic structure of the iron-chromium multilayer was revealed by nuclear resonance reflectivity using synchrotron Meuse-Bauer radiation. Reflectivity angular dependencies and Meuse-Bauer spectra were measured in the critical region. In the angular curve, the pure nuclear diffraction peak was detected due to antiferromagnetic ordering between the iron 57 layers. The combined measurements of angular and energy dependencies delivered information about magnetic structure of the multilayer. The analysis showed that magnetic structure of the multilayer was formed by the 2 spirals, one in the odd and another in the even iron layers, with the opposite signs of rotation, as seen here. At the depth of 20 nanometers, the sudden turn of the magnetic vectors by 180 degrees spin flop was detected. Deeper, both spirals started to rotate in the opposite directions. Obviously, the directionality and polarization of synchrotron Meuse-Bauer radiation were absolutely necessary to perform these measurements and obtain the unique information. Another marvelous application of synchrotron Mersbow radiation is studying single molecular magnets, magnetic molecules deposited on surface. The well-directed radiation beam allows working in grazing incident geometry to achieve the necessary sensitivity. The strong reflection occurs from the substrate. The layer of molecules works as absorber, producing absorption lines. Due to the small angle of incidence, the effective thickness of absorber is strongly increased. At the lowest temperature, the spectrum of the sample exhibits six-line structure, as expected for iron-containing sample experiencing slow spin fluctuations. Increased thermal fluctuations and the population of the excited spin levels cause a progressive collapse of the spectrum into a single central structure at 40 Kelvin. Synchrotron Mersbow radiation has provided unprecedented insights in the process of chemical absorption on a surface. Significant deformations of the magnetic core of the molecule were observed in this experiment. The observation could not have been done by other methods, neither synchrotron-based magneto-optical techniques nor scanning probe techniques. One of the most adequate applications could be studying quasi-elastic relay scattering with the high energy resolution. Demonstration of such possibility was carried out by Masuda Mitsui et al. In their experiment, synchrotron Mersbow radiation was reflected from silicon crystal that was coherently excited by ultrasound. The reflected radiation was analyzed with the help of single-line resonant absorber. The absorption spectrum exhibited the energy distribution of the reflected radiation. In turn, silicon crystal reflected the source radiation, but in presence of ultrasound, side bands appear in spectrum of the reflected radiation. The strength and number of the side bands depend on the amplitude of ultrasound. In the other experiments, the authors demonstrated studying dynamics in glassy material. It is well seen in broadening of the spectrum of the reflected radiation. Unfortunately, the potential of this method is not yet revealed in full degree. I hope it will happen in future. Unique and very productive applications of synchrotron Mersbow radiation are related with the measurements at high pressure and temperature. We consider here only one example. With the help of diamond anvil cells and laser heating, the synchrotron Mersbow spectra of hematite were measured at the extreme conditions by pressure and temperature. The analysis of these spectra gave an evidence that earth magma can be magnetism near the lower crust border at the great depth in Earth. This way, the unique information was obtained about the history of geomagnetism. Intense and small-size beam of synchrotron Mersbow radiation suggests to think about a nanoscopic type of research. We consider an application to meteorite science. You see here a picturesque mosaic slice of a palisade, a rare type of stony iron meteorite. It consists of yellowish olivine crystals in an iron-nickel matrix. Palisades have originated from mantle of an asteroid. Metallic microstructures of slowly cooled meteorites reflect the thermal and magnetic histories of their parent bodies. Of particular interest are so-called cloudy zones, and nanoscale islands in the transitional regions between different phases of iron-nickel alloy. These cloudy zones were examined with the high spatial resolution using synchrotron Mersbauer radiation. Mersbauer spectra were measured in the range of 100 microns with the step of 5 micron. The measurement time for each spectrum was less than 1 hour. Here are several spectra taken in different places of a cloudy zone. Based on the totality of all measurements, the distribution of the phase fractions of the iron-nickel alloy was obtained within a cloudy zone. Looking at this distribution, you can see what a high spatial resolution was reached in this experiment. Concluding my talk, I wish you to find your own way in using synchrotron Mersbauer radiation in your research. So, the time of summary came. A delocalized excited state of nuclei is formed of a nuclear ensemble in a crystal upon elastic scattering of a gamma-ray photon, nuclear exciton. The crystal behaves in the scattering process as macroscopic quantum resonator, with the parameters strongly different from those of individual nucleus. The internally matched nuclear exciton can be created in several spatially separated targets. A nuclear exciton is very resistant to external dynamic perturbations, provided they are homogeneous in space and time. Thanks to coherent response of nuclear ensemble, the great enhancement of radiative channel occurs. Effect of suppression of internal conversion, along with the enhancement effect, provides 100% reflectivity of gamma radiation from perfect crystals. By exciting an array of nuclei near the nail temperature in an iron-buried crystal, single-line Mersbauer radiation can be generated. It is entirely recoilless, propagating in a narrow solid angle, and fully polarized. The 4 synchrotron Mersbauer sources are operating presently in SRF, Spring 8, and in DESY, being fruitfully applied for research under extreme conditions. Thank you very much for your attention.